Hey everyone, I want to just talk about the lab that we did Thursday, Friday for lesson 2. Why don't we just go ahead and connect that first one together as we did. So I'm going to take this guy, just one bulb, one wire, pretty simple. And I'm going to adjust the voltage a little bit just so we can get some clear brightness. All right, so there's our one bulb, one wire. You can see that it's pretty bright. And then I'm gonna pause it here and rebuild the second circuit, which is, as I recall, to do two lights that are disconnecting either bulb makes both bulbs go out. That's what it said. So let's take a look at that, and we'll see what happens. Okay, so we have two bulbs that are connected in line, we'll say in series, which we'll learn about a little more later. We see that they are both a little bit dimmer than they were before, and if I disconnect one bulb, the other bulb also stops working. And you might obviously be able to see why, because both bulbs have now lost a connection to one terminal of the battery or the other. And since we have to have a continuous conducting loop, it is only when I connect both of them that they both work. Now this will be different than the way that we arrange light bulbs when we are interested in making them function independently. Let's take a look at the answer to number 3. I'm going to pause it, construct, and then I'll be right back. Okay, so I have two bulbs. I want to just show you how this works. If I connect one so that it works, and we see it's of course very bright, then I want to connect another one so that it is just as bright, and it doesn't, disconnecting one doesn't disconnect the other. So what I'm going to do is I'm just going to piggyback off of this guy, and I'm going to run a new branch this way. And I want you to watch what happens. Look at the current flowing through right now. Look at the speed and think about it, and watch what happens when we connect. When I connect this thing, what's going to happen to that current? Hey, look carefully at the first branch here. The current has not changed at all. The bulb is just as bright. All we've done is we've set up another branch. If you can see, a single electron can go through this bulb and back to the battery without ever going to the other bulb. So we have these two. These are connected, as we say, in parallel. Notice that they are both as bright as the original bulb with the one battery. Notice also that the battery is pushing twice as many electrons through it as any one light bulb is getting. That's because it's having to supply one electron to each branch at the same rate that it was applying a single branch. We'll go down to 3 bulbs that are just as bright as each other but dimmer than they are in the first. I'm going to reconstruct and be right back. Okay, here we are with 3 bulbs. Notice again they're in line. If I'm a single electron, I have to go through bulb 1, bulb 2, and bulb 3 before I can go back to the battery. I can't do an independent loop around the other two. And so as a result, we have very slow current and we have very dim bulbs because they have to share the energy of the electrons between them. All right, I'll be right back with the other one. Okay, here we have 3 light bulbs in parallel. You notice that again the battery is working 3 times as hard as it used to, and each branch is independently connected. So any one bulb can go right to the battery without ever touching the other light bulb. I'm tracing my mouse through each path so you can see that any one electron only hits one light bulb, and so every electron gets to dump all of its energy on a single light bulb, which is why they're all so bright. This is called a parallel connection. 6 and 7 were tough, so I'm gonna construct those, and I'll be right back. Okay, this is the answer to number 6. I have a very bright bulb on this side, and you'll notice when I disconnect it, everything shuts down. That's because when you disconnect right here, we're cutting off all 3 bulbs' access to the negative terminal of the battery, so it cannot work. But if I disconnect this bulb, you'll notice that the other 2 just stay as a series connection, just like before. And when I reconnect that, then I can disconnect this bulb, and there's still a conducting path through to the battery that you can see. So disconnecting either of the other two bulbs leaves the rest of the other ones on in this particular case. And you'll notice that this is a combination of series and parallel circuits. We have this whole group, which is a parallel connection of these two light bulbs, but that whole parallel connection is connected in series with the bright bulb. So we have a series parallel thing going on. Number 7 is like it, but a little bit different. I'll show you what's going on in just a second. All right, here is the answer to number 7. Notice that we have kind of a parallel connection. We have this individual branch with a bright bulb, and if I disconnect it, nothing happens to the other two. And then I have this group of light bulbs, which are both very dim because they are in series with each other, even though they're on a parallel branch with the battery. So if I disconnect this one, what do you think will happen? Ooh, notice that I waited there. Okay, let's give it a shot. All right, if I disconnect this, both of these light bulbs go out, but this one stays in. It's got its own independent connection, but this other light bulb does not have an independent connection to the battery from this, and so these two both go out while the other one stays on. But you'll notice that disconnecting just that light bulb doesn't change these two at all, and disconnecting this light bulb doesn't change this one at all. So that is the answer to number 7. We will get into the math and physics of these kinds of circuits a little later on, but for now you have discovered them all, and we'll take a look later.